Okay, this is the unit for AP Prep, things that we did not cover this unit. We are starting with number 1. For y equals x to the third minus 2x squared plus x minus 1, find the first and second derivatives, then use them to find the maxima and minima on the interval 0, 4. So, let's zoom out here. We have, just drawing out what's going on here, we have this function x cubed minus 2x squared plus x minus 1, which looks something like this. It doesn't really matter. This is 4 and this is 0. And what we're looking for are the minimas and maximas on this interval. And this is not accurate. This is not drawn correctly. But what we're looking for, okay, where is it low? Where is it? What are the places where it's high? And what are the places where it's maybe a relative maxima, relative minima? And to do this, we have to first look at what are called the candidates. So this is part of what's called the candidates test. And this is the same method, candidates test. This is the same method you would use to find the absolute max or the absolute minimum. So we look at what our options are. And these are going to be x and y values. So the minimum could be at 0. It could be at 4, or it could be somewhere in between. So we know for sure that 0 and 4 are options. When I plug in a 0, I get a negative 1. When I plug in a 4 into the equation above, right, I'm plugging in here, I get 35. But we need to find these here, basically the humps that are between the 0 and the 4. And those happen at what are called the critical points, where the first derivative equals 0. Let's start by just rewriting the equation. And finding the first derivative. And then the second derivative, just for good measure, because we will need it later. So the critical points happen when the first derivative here is 0. Because what's going to happen when the first derivative is 0, that means we have a hump, right? That what we're saying is, okay, the function is making is peaking at some point, and we have a derivative of 0, a flat line, or it could be going down. We could have a flat line in here, right? So I'm looking, where's the derivative of 0? So all I'm going to do is set that first derivative that we found up here equal to 0. So I get 3x squared minus 4x plus 1 equals 0. Factors out to 3x minus 1. X minus 1 equals 0. X equals 1/3. X equals 1. So these are my critical points right here. This one, and these are critical points. Okay, so those are the values that are going to go over here. We have 1/3 and we have 1. Okay, so what was the point? Now we have our candidates, basically our options of the minima and maxima. We can find what they are. And I can do that now by plugging in 1/3 and 1 into that original equation. You might ask, okay, what was the point in finding the second derivative? And I'll share you with that now. So this is called the second derivative test. Second derivative test. And what it says is, remember our second derivative is 6x minus 4. We can take these critical points that we found and plug them into the second derivative. So let's do that. 6 1/3 minus 4. That is negative 2. And then we're going to have 6 1 minus 4 equals 2. And the point of doing this is we get to see concavity. So reminder that this is concave down, meaning it's going to be making this shape. and this is concave up, meaning that it's going to make this shape. So since this one is concave down, that means it must be a max. And since this one's concave up, this one must be a minimum. You understand that? So it has, if it's concave down, it has to be a max. There's no way that this shape could make a minimum. And likewise with this one, it has to be a minimum because this cannot be a maximum. So I know basically that's a shortcut to let you know. Okay, well the 1/3, I know that one's got to be a kind of maximum, and the 1 is going to be a kind of minimum. That's what that's for. Anyway, so we can take these values and we can plug them into our original equation up here, and we plug in the 1/3, you get negative 23 over 27. And then for the 1, you just get negative 1. So now that I have all my outputs and all my values, I can start to identify what's what. This 4 right here, this is the global maximum. Global max, because it's the highest one, right, out of everything. So it's global max. This one right here, the negative 23 over 27, this is a local maximum. Local max. And then this value right here is going to be a local minimum. And the curious thing about this one is that because -1, these two negative ones are equal. Right, you see that? -1 and -1, these are equal. There is no global min because they're the same. Okay? All right. Moving on. That is the candidate's test. We are moving on to number 2. There are 50 apple trees in an orchard. Each tree produces 800 apples. For each additional tree planted, a little bit, in the orchard, output per tree drops by 10 apples. How many trees should be added to the existing orchard in order to maximize the total output of trees? So this is a completely different type of problem than what you've seen before. These are called optimization problems, but they're actually really closely related to number 1. We just have to basically get to the equation. They're giving us a word problem. We need to get to the equation, and then we can find the max and mins, as I just taught you here, right? We just need to get to this point first, though. So these are optimizations. Optimization. So it's worth thinking about this for a second. Okay, what's going on here? So we've got 50 trees. Right now, we're producing 50 times 800 apples. And I can add trees, but for every tree I add, the output of all the trees drops by 10 apples. It's good to sort of repeat it and sort of visualize, okay, what's going on here? Now we got to make our equations. So we have 2 variables, right? We have x, which is output, and then we have t, which is number of trees, and then I'm going to add another letter here, which is n, which is going to be additional trees. Okay, so I know that the output x is going to be 800, but we're going to have to subtract 10 for every additional tree. And then my number of trees, total T, is going to be equal to that 50 I started with, plus any new trees I add. And then my total output, so this is kind of output per tree. Total output equals xt. These two multiplied together. The number of trees times the output per tree. So you might want to pause, just refer back to that. So again, this 800 is we're given that it's 800 apples per tree. and then we subtract 10 for every tree that we add. And we start with 50 trees, and we can add as many as we want. We can add n. So the output per tree times the number of trees that we have is going to be our total output. So this is going to be, them multiplied together is 800 minus 10n, 50 plus n. When we multiply, we'll get 40,000 plus 800n minus 500n minus 10n squared. All put together, combined like terms, you're going to get 40,000 plus 300n minus 10n squared. So you can visually, by looking at at this formula, it's going to look like this, right? Because it's that negative polynomial. It's a negative quadratic rather. So it's that upside down parabola. And I'm looking for the top of it. So the way that you find that top, just like we did in the candidates test, you take the derivative, you set it equal to 0. That's going to give you the top. That's going to tell you where the maximum is. So let's do that. Derivative of this is negative 20n plus 300. I'm going to set that equal to 0. Move the 300 over. We get negative 20n equals negative 300. And then just divide by negative 20 on both sides, negative 20 on both sides, n equals 15. So this right here, if you can picture this on a graph, this would be at 15. So we would want to add 15 more trees. Would be optimal. Okay. And we answered the question because it just asks how many trees should be added. If we wanted to find that output, you would take that 15 and plug it into our output equation, which is either this one or the multiplication one. It's fine. Okay. All right. Number 3. Car B is 30 miles directly east of car A and begins moving west at 90 miles per hour. At the same moment, car A begins driving north at 60 miles per hour. What will the minimum distance between the cars, and at what time does the minimum distance occur? Okay, this one, I'm going to add a new piece of paper here. This one is, again, it's also an optimization problem, but it's a little different because it's not... I guess the first one is kind of an economics-based one where you're looking for it's sort of the same as max profit, kind of. It's like optimization of output. This one is kind of geometric. So we want to draw it first before we do anything. So we're starting with 2 cars. We have, let's say, car A is right here. And we know car B is 30 miles east of car A. This must be car B over here. And we are moving, so car B is moving west, right? This. And car A is moving north. Like this. And at some point, as these are moving, so this is, I'll draw kind of an arrow to show that. It's an arrow here, it's an arrow here. At some point that we want to find when is there the smallest distance between the cars and what time does the minimum distance occur. So we have the distance between them, I'm showing by this additional line here. So this is where it is kind of arbitrary on this line here, but this is going to be the distance between them. A could be anywhere along here, B could be anywhere along here, and the distance between them is what we're looking for. We're looking for this to be the smallest as small as possible. So I'm going to call this distance here. What we have, luckily, is a right triangle. You can see that here. And we're going to call this distance A. And we know that this whole distance here from A to B is 30 miles. That's given to us. Therefore, this distance here is going to be 30 minus whatever the car has traveled. Okay. And then that means through Pythagorean theorem that through a squared plus b squared equals c squared, this must be the square root of a squared plus 30 minus b squared. So just to recap that, A is distance car A traveled. B is distance car B traveled. And then we're going to have a new variable here, which is t, which is time since start in hours. Okay, so the distance at A, let's start with A because A is kind of easier. Well, we know that the car is traveling at 90 miles per hour. So the distance it's going to be traveling is got to be A is 90 times T, times how many hours we've gone. And then for B, oh, sorry, A is going north at 60. So, sorry, A is 60. That's my mistake. A, it says here, moving north at 60 miles per hour. It's B that's going at 90 miles an hour. B is 90T. Okay? 90 miles per hour times however many hours we've gone. So we're just going to substitute these values into our equation. So we're going to get square root 60T instead of A squared plus 30 minus 90T squared, which becomes, 11700 T squared minus 5400 T plus 900, all square rooted. So this function here represents the distance between the two cars. So this is, now that I got the function, if we look at number one, now I have this. I got my function. Now I'm going to derive and set it equal to 0. Okay, so we got to take the derivative of this. Derivative of this, because it's the 1/2 power, is going to be, let's call this, I don't know, we'll call it y prime, equals 1/2 11700 T squared minus 5400 T plus 900 to the negative 1/2 times the derivative of the inside chain rule, 23,400 T minus 5,400, which, when we simplify this, looks like 23,400 T minus 5,400 all over 2 root 11700 T squared minus 5,400 T plus 900. And all this is going to equal 0. And we can multiply both sides by the denominator. Basically, for this to equal 0, just the numerator has to equal 0. So you can multiply both sides by the denominator, and you'll get, I'll just show you what's going on there. This would be multiplied by 2117, and then the root 00 t squared minus 5400 t plus 900. I'm just multiplying so that these cancel, and I'm doing the same on this side, right? I'm multiplying by 2,11700 t squared minus 5400 plus 900. Same thing. And then that just becomes 0. So I'm allowed to do that. So all I'm now left with is 0 equals 23,400 t minus 5,400. Solve that for t. Move the 5,400 over. T equals 5,400 over 23,400, which equals 0.23. So minimum distance happens at t equals 0.23 hours, right? It's about a quarter of an hour nearly. And then to find the distance, we're going to take that 0.23 and plug it back into our original equation. So when you plug it back into the original equation, you get d equals 24.96 miles. And that is number 3. Okay. Number 4. You are standing at the edge of a slow-moving river, which is 1 mile wide, and you wish to return to your campground on the opposite side of the river. You can swim at 2 miles per hour and walk 3 miles at 3 miles per hour. You must first swim across the river to any point in the opposite bank. From there, walk to the campground, which is 1 mile from the point directly across from the river from where you start your swim. What route will take the least amount of time? Okay, so this is the situation. I think the question doesn't do a good job of sort of explaining what's going on. This is you here, and we've got a river like this. So this is like the river. Imagine, okay, we got a river here, right? And it's 1 mile long. And then you've got another mile over here to your campground. This is your campground. And then, I know it's not to scale, this whole thing is 1 mile. So you can swim at 2 miles an hour and you walk at 3 miles an hour. So you can choose to swim directly across and then walk down, or you can choose to swim to a point along here and then walk down. And that's the idea. So we're looking, instead of going across and over, that's long. We want to find some way of cutting across, swimming part of it, and then walking down to do the rest. So we don't know this distance. We just know that this is going to be x. And then this distance is going to be, it's 1 mile in total. So it's 1 minus the x here. Okay. Which, again, this is Pythagorean theorem. That means this section must be the square root of 1 squared plus x squared. So that's 1 plus x squared. That's Pythagorean theorem. 1 plus x squared. So the total time, t of x, is going to equal that 1 minus x. So whatever 1 minus x is, this distance here, divided by 3, because we're going at 3 miles an hour, plus this distance right here, root 1 minus x squared. 1 plus x squared. Okay, sorry, took a little break there. So yeah, this is all good. This is going to be over 2 because we're moving at 2 miles an hour in the water. And then this can be simplified to 1 over 3 minus x over 3 plus 1/2 root 1 plus x squared. And so now we've got, like, once again, this was honestly the hardest. This is the hardest part, right? Now we've gotten to the function. Now we know what to do. Now you understand, like, okay, I just need to find where this equals 0 to find the best point. And it's the same thing here. We got to the equation. Now we take the derivative. So the derivative here is going to be negative 1/3 minus x over, minus 1/3 plus 1/2 times 1/2 times 1 plus x squared. This should be a 1 to the power of negative 1/2 times the derivative of the inside is 2x. Just to break that down for you, the 1/2 is right here. This 1/2 comes from taking the 1/2 down up front. This negative 1/2 comes from subtracting 1 from that, and the 2x is the derivative of the inside. Okay. This then simplifies to negative 1/3. Oh my goodness. Negative 1/3 minus x over 2 root 1 plus x squared. Okay, so when you combine these together, when you do the multiplication, that's what you get. We're going to set that equal to 0. Because remember, that's the whole point of this. Move the 1/3 over. We're going to get 1/3 equals x over 2 1 plus x squared. We're going to cross multiply here. This is negative. We're going to cross multiply here, so we're going to get 2 root 1. Sorry, the recording cut out there. We had just cross multiplied, and we should have gotten this. And then we're going to divide both sides by 2. So we'll get root 1 plus x squared equals negative 3 over 2x. Then we're going to square both sides. And we're going to get 1 plus x squared equals 9 over 4x squared. And then I'm going to move my x squared onto one side. I'll get 1 equals 5 over 4 x squared, because that's basically minus 4 over 4 x squared there. And then we will multiply by the reciprocal. So multiply by 4/5, multiply by 4/5. So 4/5, that means it's cancel. So 4/5 equals x squared, square root. So x equals the square root of 4/5. So visually what happened there is, back to the drawing, we want to be 4/5 of a mile to the right, or the square root of 4/5 of the mile over from our from this point towards the campground to optimize the distance. Okay. All right, continuing on. This was on the test. This is the extra credit problem. The height of an object, you're given the position and the height, and then you want to know when does it reach maximum height, what is velocity when t equals 2, and what is velocity when the object hits the ground. So I think it's really important, and a bit of a review here is this relationship between position, velocity, and acceleration, and how you can move between the two. Remember, you can always move this way through deriving, and you can taking the derivative, and you can move this way by this is integrate. Okay, so look, I'm given position, right? So to get velocity, I need to take the derivative. So for d, I mean, so many people on the test just plugged in a 2 into this and called it a day. But this is the height. This is not velocity. I did not give you velocity. I gave you height. You had to derive it first. We'll get to that. We'll move to C first. What's the maximum height? Well, this is exactly the same as all the other problems. We have to find the derivative first. Let's do that. So the derivative is negative 32 t plus 100. The t's and the pluses, man, they are horrible, aren't they? Jesus. Okay. Then, just like the other ones, visually what's going on here is you're finding where it hits the peak. So we just need to find when this is 0. So we have negative 32 t plus 100 equals 0. That's 100 equals 32t, and then divided by 32, divided by 32. So t equals 100 over 32. So that's the time of this, 100 over 32. And then we got to plug it in to get the height. So when you plug that in, and then this does not go into velocity, this goes into the original. When you plug in 100 over 32 into this equation here, you're going to get 356.25. So again, if you're wondering where I got this 356.25, you take the 100 over 32, you plug it into this right here, and that'll get you the 356.25. B. So okay, B is easy. We have velocity. Velocity equals negative 32t plus 100. So what does it equal when it's 2? Just plug in a 2. It's negative 64 plus 100 equals 36 meters per second. Okay. And then C or E here, what is velocity of the object when it hits the ground? This one's, I find this one really interesting. So back to this example, it looks something like this, right? So I'm trying to find what is the velocity here. Velocity, what is it here at this point? Well, I need to know where this point is. Just like how I found this point by setting the derivative equal to 0, I need to now find this point. It's also kind of recall like this is an axis. So what we're going to do is set the original equal to 0, right? So we're going to have negative 16t squared plus 100t plus 200 equals 0. And you can use whatever method you want. Quadratic formula works here. Graphing works here. But that value ends up being t equals 7.844. That's the time. And then to find the velocity, you take this and we're going to plug it into our velocity function. Velocity equals negative 151.008 meters per second. So how did I do this? You set the original equal to 0 and you solve that through graphing it, or you can use quadratic formula. You get this new time, you plug that time into the velocity function to get the velocity. Okay, we're on the number 6 here. Miss Ligsay tossed a piece of chalk to Quinn, who was about to take a presentation. Velocity of the chalk with respect to ground. Now this time we are given velocity. Okay. This time we are given that. We're given velocity is, we have t equals negative 32t plus 10. And first question is, when was it 0? Well, this one is easy. Just set it equal to 0. Less than equals 0. Subtract 10 from both sides. So you got negative 10 equals negative 32t. So t equals 10 over 32. So that means that's when the velocity was 0. And the velocity 0, again, visually, this is what's going on. It's this point. Velocity is 0. Okay. Max height. Next question. Find A. So back to what I said before. If I can find that paper now. Yes, here. Look, we're given velocity. We're asked for acceleration. Take the derivative. We take the derivative of this. We get, so the derivative of velocity equals acceleration. So A of t equals just negative 32 feet second squared. C. If S of 0 is 5 1/3, find a function that represents the position. Okay, so position, you should be thinking integral. So we have velocity. Look, we're going to position. We need integral. So my S of t is going to be the integral from 0 to t of velocity, v of t, plus that starting position, 5 1/3. So the S of t will be negative 16t squared plus 10t plus 5 1/3. This is like the C, if you can picture that. The 5 1/3 is the C. Okay. D, the last one is on the back here, or I. Find the time t at which Quinn caught the chalk when it was 6 feet off the ground. So here we have our position. Now we're going to set that position equal to 6 because it was 6 feet off the ground. So 6 equals negative 16t squared plus 10t plus 5 1/3. And then we're going to solve this. So set it equal to 0. 0 equals negative 16t squared plus 10t minus 2/3. And then you can do this by graphing or quadratic formula, and you will get point t equals 0.55. Okay, 0.55. Okay, last page here. This is an FRQ. So this is from the 2016. Yeah, this is the 2016 test. This is number 6, just in case you were curious. So it's actually like fairly straightforward if you know what it's asking for. So, okay, so you've seen this before. You've seen this on delta. We have a table of values. We have the derivatives and outputs of those different values. And we have our first question here, we have a k, and we want the equation for line tangent to the graph of k at x equals 3. So whenever you see line tangent, you should be thinking in your head that equation that we learned way back when, which is y minus y1 equals mx minus x1. Okay, that should be ringing around in your head whenever you come across a problem that's talking about a tangent line. And now we are just here to find the values. So, well, we know our x is 3. So this is like our x1. Our x1 is 3. Let's go ahead and find our y1 because while we're at it. So our y1 is going to be f of g of 3. So g of 3 is 6. So f of 6 is 4. So y1 equals 4. Okay, so I plugged in a 3 for g, and I got 6. Then I went to plug in 6 for f, and I got 4. Okay, so I've got my y1, I've got my x1. The last thing I need is my m. So I need slope. I need k prime, which is going to be so this is chain rule. So it's going to be the derivative of f at g of 3 times the derivative of g of 3. So g of derivative at 3 is 2. And then g of 3, we already know that that's 6. So the derivative of f at 6 is 5. So we have 5 times 2 is 10. That's my m. So now I have all the pieces. I can write it as y minus 4 equals 10 x minus 3. Okay. Next, this is very similar. This is b here. We have h of x equals g of x over 3 of f of x. Sorry, this is quotient rule. Quotient rule. So quotient rule says it's going to be f of 1 g prime 1 minus g of 1 f prime 1 all over f of 1 squared. Weirdly here, I think this is kind of strange. It's like we're used to seeing quotient rule written as f of x over g of x, and this is g of x over f of x. So it's almost like, I don't know, trying to confuse you for that, but it's just low goes first. So that's why it's f of 1 comes first, because f of 1 is the denominator. That's what matters. The denominator needs to come first without the derivative. And when you do this, you will get negative 6. You just go find the values. Negative 6, 8 minus 2 times 3 all over negative 6 squared. This simplifies to negative 3 halves. Okay, the last one here, this is fundamental theorem of calculus. Sorry about the stain left. This is f prime of 2x from 1 to 3. However, we haven't learned this yet, so I'm not expecting you to know this. This is due to a thing called u substitution. This ends up being a 1/2 out in front here. So that's the only difference. The thing that you don't know how to do is that. So this then simplifies to 1/2 derivative of 6 minus derivative 2, which is 1/2. 5 minus negative 2 equals 7 halves. And that's it.